y1, comma x2 plus y2, comma x3 plus y3, comma x4 plus y4, dot 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 xn plus yn. That will be my resultant vector. Okay. Now, how do I take a mean? Means averaging. So I take the size of the cluster as the mean. So if you see, this will again be an n-dimensional vector. So this is my cluster center. Clear till this point? Yes, no?
Yes, ma'am, clear.
So then we are having cluster center distance measure. We understood what is mean by like measuring closest to each center or each point. So as you can see that the cluster centers are nothing but yet another pseudo data points on my data plane, right? So now as we are doing clustering, we need some kind of loss function, right? So what is our loss function? It is defined as the k means loss. So this is the distance of the data points from particular cluster center. That is the sum of square distances from each point to the associated cluster center. So what we are saying is like assigning a data point to its closest cluster and repeat the process until the data points are not changing. That is defined by the loss function. So the loss is equals to, and in k means everything is based on distance. So what will be my loss? Loss will be if my distance is of a data points is very high from a cluster center, that will be my loss. So the loss is defined in terms of the distance and by the yes, the square distances between a data point to the associated cluster center. Okay. Clear till now? And why the square distance? Because distance is a square root. So distance is root over, right? The Euclidean distance. So if you take a square, that means basically this root is gone. This quantity comes out. So what is my running time of k means then? See, for every iteration, I need to do two things. So finding the first cluster center is constant. That is a one-time job. Now, I need to assign each data point to the closest cluster center. So that means I need to compute the distance of each data point with each of the cluster centers. So if now there are k cluster centers, that means k distances for each point. And if there are n data points in my data set, that means totally order of k into n times. Okay. And then when we need to change the cluster center by averaging over the cluster members, that is the order of n, because across all the clusters we need to do n calculations, that is adding up at most n elements, and then division is constant, right? Division by the cluster size is constant. So this is my running time of k. Now, as what are my big issues for k means? Of course, first is my value of k. How do I know the number of clusters? Second is the my convergence criteria. So I can take one of the three, either a fixed number of iterations, either partitions are unchanged, or my cluster centers do not change. So the examples that we have seen there, when the partitions were unchanged, we stopped the clustering. And then, as someone very rightly pointed out, the initial or seed cluster centers for K-means. Like, because everything depends on the initialization. First, let us address these issues one by one. Value of K. So ideally, what do? We plot different values of K and the K-means laws. So this y-axis is the K-means laws and this axis is the values of K. So we run different run clustering on the data sets with different values of K, and as someone was asking that if K is the hyperparameter, if you run a code that is computing the different K-means laws over K, then it is a hyperparameter. So you are now tuning K. Okay. So this ideally this loss versus K plot should look like this. And so see, this is like a graph elbow, right? It is like someone's hand, like in our hand, the elbow looks like this between the forearm and the arm. So at this point, this is a good value of K to cut, because at this point, for this particular K value, I am almost reaching the minimum of the loss, and also if I keep on increasing K value, I don't stand much to gain. So I cut at this point. So in this case, say that K is equals to 3. This is the elbow method to identify K. There is another measure which is used more, that is called the silhouette measure. So what does silhouette means in English? That is the outer shape, right? Or the outlines or the shape. So we will follow the same thing, like that's how the name has come. So for a good cluster, what are the two key things? That is my within cluster variance. That is data points within the clusters, they will vary small, and between clusters, like across the two clusters, there will be large variance. So with our silhouette measure, we try to ensure this. So basically, we create a like hypothetical outline between the of the clusters, right? That this is my cluster boundary. So we have small within cluster variance and large between cluster variance. So how do I come say within cluster variance? So if Ci is my cluster for data point I, my within cluster variance is basically distance of I with all the other data points in the clusters, and that is normalized by or averaged by Ci minus 1. Why minus 1? Because this I is 1. Okay. So basically what I am doing, I am taking the average distance of I from all the other data points in the same cluster as of I. That is my AI. If you need some time to write it down, please let me know. But please write it down, because I know this seems very intuitive, but trust me, when you actually close the presentation and will try to write, it will find a difficulty. And for 2 years, you people have not written offline exams. So please take the effort and write it down. Okay. Okay, so this is my first within cluster measure. Then, as I said, there has to be a large between cluster variance. So how can I come up with a between cluster measure? So for all other clusters than Ci, say for Ck, I come up with the distance of I with all the other data points in the cluster Ck. See, in this case, J belongs to Ci. That is the same cluster. In this case, J belongs to Ck. And I normalize it with the size of the cluster Ck. And I take minimum over all the K clusters. That is for across cluster for I. So in this case, we are taking, so this measurement I is at the level of the data, sorry, this measurement of silhouette measure is being done on a particular data instance. So for a data instance, what will be a between cluster measure? That is the distance of the data points from the second nearest cluster. Like say I say you are a data point. You are in a particular cluster. Say your cluster is your home. So you are at your home. So what will be your distance from all other neighboring homes? So in your neighborhood, there are say like 4-5 homes, like 4-5 clusters. So basically that you will say that I am at least this distance away from my next home. So that means among the 4-5, you are measuring your distance from the neighboring homes in terms of the minimum. So basically, now to have a good clustering, what we are trying to do, we are trying that this will be minimum and this will be as large as possible. So my data instance I will be very compact within its own cluster and also will be distant from other clusters even when taken the minimum. Okay. So the silhouette measure is exactly defined in terms of them. That is Bi minus
Ma'am,
Ai. Yes.
in the constant for the minimum for BI, it will be I does not belongs to CK because K is a cluster number and I is the data point number.
No, no,
Like
I is also the cluster number. See, so what we are saying that data I belongs to cluster I. Okay, that is CI. So it is just
so then Dij. So Dij, the definition for Dij will be different in that case because for every I belongs to the cluster I, we have to compute its distance with for every j belongs to cluster j.
this one.
No, ma'am. In
This one.
the next, yeah, yeah.
Yeah, no, not for every I. So this is just for one I, right? So for this I, we are calculating its distance for every j belonging to the cluster K.
Yeah. So the I in the parameter, the I which is passed as parameter in B. So that I is for data point or for the cluster.
No, here, so this is not parameter. This is we are just taking minimum over the all the clusters like K, where K is not is equal to I. So I think the confusion is because like the I is also denoting the data point and I is also denoting the cluster. So we are saying the data point I is belonging to say to the cluster Ci or the cluster I. So that is why it is written K not equals to I.
Okay, ma'am.
Okay. So my silhouette measure Si is dependent, is defined as Bi minus Ai by maximum of Ai and Bi. Okay. And the condition is if size of Ci is greater than 1. Because see, if size of Ci is equals to 1, that means what? I have only one vertex I in Ci, or sorry, only one data point I in Ci. I have told vertex so many times, and now even I am missing. Okay, so if it is just one point, then Si would be 0 because that means this is an isolated node. Okay, so we are not doing any measurement on that. So this is how my silhouette measure is defined. Is it clear till now?
Yes, ma'am.
So property of the silhouette measure. So how do we find desirable values of K? Again, we take the average silhouette score over all the data instances for n data set. This is n data points. This is defined, and we again plot the average silhouette score versus K. And in this case, the higher the score, it is better. because silhouette score is like if Si is equals to high, that means Bi is much larger than Ai. That means between cluster measure is much less larger than the within cluster measure. So it is satisfying my these two conditions. So for silhouette score, so that's why it is a score, not a loss. Okay, it is a score function. So the higher the score, this is my desirable value of k. So see, approximately at k is equal to 3, we are reaching a peak of the silhouette score. So we are saying that this is my desirable value of k. Okay.
Ma'am, for the Ci equals to 1 in the previous slide, how the seal out measure is turning out to be 0?
Tell me.
Ma'am, it should be 1, right?
How will it be 1? Okay.
Ma'am, because the inside the cluster there is no other point, and then the AI can be thought to be 0, and so it will be Bi upon Bi,
Yeah,
something like that.
yeah, it will be 1. Yes. So actually, this is like this is your equation if Ci is greater than 1, but this is your value. So it is kind of like a condition that if Ci equals to 1, then my Si will be 0. So this is not following from this. This is my criteria for isolated data points. Okay.
Okay, ma'am.
Because then either my data point is outlier or somehow the clustering is not done appropriately for this data point. What you are saying is very correct. It should be 1, but this is a defined criteria that if Ci size of Ci becomes 1, then my Si will be 0. Because see, if size of Ci becomes to 1, then you won't be able to come up to this equation because this will become something undefined, a division by 0.
Yes, ma'am, and also the isolated cluster is not a good one, because after all, for too many clusters the loss will be less.
Yes,
And
yeah,
is it the reason that why the in the K means sorry, in the elbow method we are also not going down the elbow line after a
yes,
certain.
yes. This is the reason that we are not going down because see, we are not gaining much. But if we are having too many clusters, then there will be also like the chances of the error and noise that also increases, right? Because it will not be very likely that with this much of gain, like your data set will have 10 clusters. Okay. So that's why we are cutting it here. So it is kind of a like trade-off that we need to do. Is it clear?
Yes, ma'am.
So now my value of k. Now my second part is the initial or seed cluster center. That how do I come up with the initial cluster center? First, the most common approach is to initialize cluster centers randomly. Now, say for example, randomly, if I say these three are my cluster center, then what would happen if I reiterate the process of k-means? So it will come up with 3 clusters like this, because see, no matter how many iterations I run, this cluster's boundaries won't actually change because there is nothing to change, because clusters boundaries only change after assigning and recalculating the mean only if there are other data points. So if we initialize randomly and if my initialization is not proper, then I come up with bad clustering, as someone was rightly pointing out. So the choice of the initial centroid in k-means is very important. So results can vary drastically based on the random seed selection. It can be either very slow convergence or it converges to suboptimal clustering, like we have seen in this example. It will converge quickly, but this is not the cluster that we want, or that this is not the cluster that is useful, right? Okay, so another thing, centroid means actually mean. Centroid is the main center of gravity, right? So that is in this case for a cluster, because all these notions comes from like a clusters being a in a like a spherical thing in the n-dimensional space. So we interchangeably use the centroid and the term means. So what is the common heuristics is random. We pick random centers in the space. We randomly pick from features vectors, and we have the farthest centers heuristic, that is like we pick some points which are least similar to any existing center, and we try out with multiple of these points, and or we initialize the results with another clustering method. So this is not steps. Okay, these are different heuristics. So first one is, as we have seen, we pick up random centers in the space. Second is that instead of picking up random centers, we actually pick from the data instances. Like we take some of the data instances to be the random centers, which we generally do. But again, we pick randomly. Third, what we go on doing is that what is also called the farthest centers heuristic. We pick random centers, then we also pick points as centers which are least similar to any existing centers. So say for example, I take the first centers that I pick randomly, but the second center I assign that the point in my data instance which will be farthest from the first center. So the idea is that if we pick farthest centers, then the more possible, more probable it will be to have a good clustering. Because if the centers are farthest, that means the data points will also be clustered accordingly, and like not majority grouped in the same cluster as some 2 or 3 grouped in the another cluster. We try out from multiple starting points, like we iterate over multiple clustered centers, and or what we can do is that we can run another clustering method and come up with probable cluster centers, and we initialize k-means with those cluster centers. So we come up with hat and we run hierarchical clustering, and then we initialize the k-means with the hierarchical clustering. So let us see what does farthest centers heuristics means. So say I pick the first center randomly, which is mu1. For I equals to 2 to k, where 2 to k is the number of the clusters, that is why I is initialized at 2, because I have picked the first cluster center. Say for example, my k value is 5. So that means I have picked the first cluster center, but I still need to pick the other 4 cluster center. How do I pick the 4 cluster center? For the second cluster center, I pick the point that is farthest from mu1. For third cluster center, I pick a point that is farthest from both mu1 and mu2. For fourth, I pick which is farthest from mu1, mu2, mu3, like all or any of the 3, and in this manner, I go on picking the 5 cluster centers. So let's see for k equals to 3, how do I pick this? Pick a random point for the first center. Say this is my random point. So then for the second cluster center, what did I say? That we will pick the farthest from this first center. So which point will be chosen next? This point is the farthest from this in the data set. So this will be my second center. For third, it needs to be farthest from any of these 2 or either of these 2. So it will be my third cluster center. But what are the concerns or issues with this approach?
Ma'am,
Yes,
how do we
yes.
get a point which is farthest from 2 or 3 points? Like, how are you exactly uh, determining that point? Means
Okay.
farthest from one point we can get by computing all the distances uh, with one center. But from two centers, how are we taking the two distances into account?
How did you do it in the coordinate geometry? That come up with a third point, which is distant from two other points in
I'm
the space.
taking the maximum distance of that.
In the basic, so see, we can compare the distances. Say for example, if we take this point, so what will happen? This will have a very high distance from this point and not from this point. But if we take this point, this has almost like large distance from this point as well as from this point. That's how like we go on comparing and we come up with it. Okay.
Okay, ma'am.
But anyway, just remember the criteria is that farthest from any previous centers. So ideally we try to satisfy all, but as you are saying, say like if my k is equals to 5, then it may not be possible always to satisfy it for all the previous fours, but maximum farthest point. But what is the issue with this approach? Because this looks very nice, right? For this data set, for this plot, the based on the first initialization that we did, so it looks that it is actually grouping the data set very nicely into the three clusters, and it will converge very soon, and it will also give me nice clusters. But what is the point? Say for example, if my data set looks like this, and now I start with the first mu1, this. So what will happen? My first cluster center will be here. Second maybe here. Third will be here. So it will be going on like this. So now my clusters will be, this will be a big cluster, this will be a cluster, this will be a cluster, and this will be a cluster. So it doesn't deal well with the outliers or the data points which do not follow the pattern. And in the real world data, actually we have a lot of occurrences of outliers. Okay, so this is one of the drawbacks of the farthest point approach. So a better approach where we actually use some information to initialize the clusters is called the k-means plus plus. So in this case, the centers are initialized using a probabilistic approach. The other steps are exactly same as the standard k-means, only the first initialization differs. So instead of just randomly speaking, we are taking the help of the probability. How do we choose? We choose one center C1 randomly from the data. Now, for each point in the data set, x belongs to capital X, we compute the distance. Distance of x from the closest center we have already chosen. So, now we select the new center with the probability, say our data point x has the probability to a new center based on this. That is gx square, again square because distance is defined in terms of square root in Euclidean space. So square removes the square root. So basically distance of x from the cluster center, the first centers, which is divided by all the distance of all the x from the first center. So this is now taken as the probability for for a data point x to be the new center, and we repeat So basically then the data point which has the highest probability will be chosen as the cluster center, and we repeat the process 2 and 3 until all the K centers are chosen. So let us see, just a second. So let us see how it affects, like how does it deal with the outliers. So say for example, if I want to create 3 clusters, so I randomly pick the first center. Second, I calculate this dx for all the x in my data set, and I also calculate the probability. So this becomes most likely to be my second center. And then from these two centers, I converge to the third center, which will be most likely to be my third center. Anyone? Any question? Can anyone answer me this quiz?
Black line.
Yes, why black line?
Because the closest center is the first center.
Yes, the closest center is the first center. Good. So, anyone has any question over this K means plus plus? Okay. 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 So then let us see how, say for in the same example, how my K means plus plus would have helped. See, if I start with these random centers, and then if I calculate the distances, like this is with the this point, so all of this for the first step at least, all of the distances will be calculated with respect to this, right? But then when I, like now, instead of farthest center, what I am doing, I am normalizing the distance of a particular data point by the summation of all the distances. So even if my distance is very high, but when it is normalized over all the points, the probability that an outlier will be picked up as the second center will decrease. Okay. So we have completed spectral clustering today as well as the K-means. So any question from any of these?
Ma'am, I didn't understand how it helped, K-means plus plus helped in the outlier case. Can you explain that once again?
See, we are defining the probability based on not only the distance of the point with respect to the first randomly picked center, but the distance of the point is actually normalized by sum over all the other distances of the points. So basically, if a distance is very high, so but if that is the only point, if that is the outlier, say this point, this has very high dx. But when I normalize the dx with sum of all the other dx's, its probability will not be that high to get chosen as the second cluster center. So that is the intuitive understanding. Now see, no approach can guarantee like 100% that no outliers will be chosen, but we are again maximizing our chance as much as possible.
Ma'am, but in this case, the I understand that the outlier will have the choosing probability of the outlier will be less than compared to other methods, but the other points will have even lesser probability, right? So, like ultimately, we have to choose another point. So, how will the K-means plus plus proceed again?
Yes, the thing is that this may be the one discrete example that you see where you feel the k-means plus plus will not hold up to the outliers. But the idea is that in the real world setting, the probabilities are very close to each other. Or like if you when you are averaging over a larger number of points, the idea is that a point being actually a cluster center or belonging to the cluster will have a higher probability than an outlier. See, this is an experiment, like just a data set representation done actually to show the demerit of the furthest point hypothesis. Okay, so this is not any actual data set representation. So what I'm trying to say, like in real examples, when you are doing it, say over like 5,000 data points, then actually, if we take this kind of probability measures, so the chances that we will pick actually a point which is not outlier is higher.
Okay, ma'am.
Any other question?